really say what's the best for the human. There are some like very subjective metrics that you should take into account. So the idea here is that we do our best by defining this cost function that is like it's reasonable. But then of course, like it could happen that it could also happen that the human is actually not happy with the solution, so that it's optimal for you with your optimization cost, but then it's not optimal for the human because there is something we are not able to model. So the answer is that we do our best, so we do what we consider that could be optimal. So, but of course, then there might be issues in actually considering what the human prefers. And also there could be issues in feasibility. So the idea is that you could do your best, then you try to be as close as possible to the optimal solution that you believe. But so actually also in the reallocation strategy, we don't go for the fully optimal solution. So we, because since we are using a MILP problem, we have NP hardness computational issues. And so we don't run every time the MILP, but we do have a kind of heuristics just to understand if the new, the plan with the new parameters is still okay or not. So we are not always fully optimal. Thank you.
Okay, so it's time to move next speaker. Thank you so much. Okay. Cool. So our next speaker of this session is Rafael de la Guardia. I think it should be already. Oh, perfect, perfect. Okay. So Dr. Rafael de la Guardia from Intel Corporation. I think a company that's shown amazing human multi-robot shows, and which is also sponsoring the awards to this workshop. So Rafael, I think, yeah, you already should share your slides. You can start whenever you're ready. Yeah, I think your mic is off in case you didn't realize.
All right, so sorry about that. Is it working now?
Yeah, now we can hear you. Thanks.
Great. So let me share again. Are you able to see my foils?
Yes.
Oh, great, thank you. All right, so today I'm going to talk about collision avoidance for multi-robot systems. So where we have robots that need to react to unknown obstacles because the environment is not known a priori, and the robots have a limited sensor range. So we consider here planning-based solutions that take into account the constraints from the higher order systems, in particular MAVs, which stand for micro air vehicles. And in our case, it's mainly quadrotors. So, but sorry, I want to acknowledge my co-authors, Leobardo Campos, David Gomez, and Jose Parra. We are all in the Human Robot Collaboration Group in Intel Labs, located in Mexico, in Guadalajara. All right, so we are interested in multi-robot systems, human multi-robot systems, because we think that robots can augment the capabilities of humans. So in this video, for example, we have from our this video, by the way, is from our colleagues Javier Felipe and David Gonzalez. And you see a use case where the Javier here is assembling a computer server. So installing memory modules, the CPU, and so on. So he has a robot helper that is able to to accomplish some of the tasks. So the reason that this problem helps, or what we want to illustrate here, is that by partitioning the task in a way that we can take advantage of the capabilities of the robots and the human as well. So the robot can help Javier accomplish a task faster, and it can also, for example, hand tools because the robot is keeping track of the task that is being performed, and it can sense that the appropriate time when the person is going to need a tool. So in this sense, the robot here is extending the capabilities or the reach of the person, because he doesn't have to go all the way around the table to grab the tool himself. So what we want to do is use this idea of augmenting the human capabilities with robots, but now using MAVs. So the MAVs have limited capability to manipulate the world, but they are able to extend, for example, the senses of the person, right? So they can, for example, have a different viewpoint that allows them to see beyond the obstacles that the human is not able to see beyond. They can also look 360 degrees around the person, or they can look at objects of interest that are very high. So here, for example, we have two drones that are being controlled by the human here. So the person is carrying a camera on one hand, and he's carrying a beacon in his other hand. So the robots, what they're doing here is orbiting around the beacon that is hand carried by the person. So the robots can be carrying cameras, for example, as I mentioned, to perform some inspection or other kind of task. And the beacon itself, in this case, is a physical object that is hand carried by the person, but it could also be a virtual beacon, like something that the person controls in a computer screen, or even gestures that can be the person pointing to a particular object of interest, for example. So the task that we want to solve in a cooperative way with the maps is to follow a virtual beacon that is controlled by a human, while avoiding obstacles with each other and with other obstacles. Optionally, also maintaining a formation. And I'm going to describe 3 strategies that we have developed and implemented by my team. So I'll start with the first. Is based on a limit cycle. So in this case, the idea is to create a closed loop control protocol that is distributed and that provides guarantees for the robots to be able to converge to a target that may be moving around. They can do so avoiding collisions with each other, and maintaining, arriving at the formation at the end, and also optionally rotating around the target while maintaining the formation. So the mathematical expression of this protocol is shown here. I'm not going to go into much detail. I just want to mention that this is a composition of 4 different separate controllers that are decoupled and then put together in a way that maintain safety guarantees. So one controller, for example, takes into account the rotation velocity that is desired around the target. Another one takes the position error with respect to the radial distance between the agents and the target. Another takes into account the angular separation between the nearest neighbors of each agent to arrive at the formation. And the final one is in charge of maintaining a minimum separation between agents. So we implemented this strategy in a gazebo simulation environment using model drones from a plugin gazebo that is called Rotor S, that comes from ETH Zurich. And so you can see here I'll play it again. The swarms of the group of drones start from arbitrary position, and they are able to converge to the desired formation and rotate about the target. So I'll move on to the next strategy, called these motion primitives. And in this case, what we assume is that the robots have a limited sensor range, and while the target may be beyond the current field of view of the robot, our task is to provide or to find points that the robot can reach and that they are known to be safe because they are inside of the field of view and they are collision free. So in order to reach these points or these waypoints that will take the agent closer to the target, the agent is going to follow a motion primitive, which is the F1 trajectory, that in this case comes from the solution of an objective function. So we want to find the objective function is given here by the letter C, and what we want to solve is the trajectory that will take the robot from an initial position at time t0 to a final position at time t1 in a prescribed time, capital T. And because the robots are drones here that need to have continuous derivative up to jerk, so up to the third derivative. So this is achieved by minimizing the square of the snap, which is the fourth derivative. And the result of this optimization problem is a seventh order polynomial that can be parameterized in terms of the initial state given by the position, the velocity, and the acceleration and jerk at the initial time, and the final state and the time, capital T. The final state we can choose arbitrarily. So we do that finding a point in the map, in a map that is available to the agent, and where we can find a point that is in free space or in the safe space that the robot can reach. And it will require that when the robot arrives at this point, it will have zero derivatives. So velocity, acceleration, and jerk are all zero. So this is a point where the robot can stop safely and, for example, replan if necessary, or continue, or just stay there if he already arrived at the target. So in general, this is not going to be the final target. So what we will want to do is, at some point, while the robot is traversing the trajectory F1, it will have to replan. And because it has moved, the field of view is able to see further now towards the target, and we can find another point that will move it closer to it. So the task then is to connect the new waypoint with the current trajectory. So we need to find the time, which is called here T2F, such that the new point that we find in the free space that is currently in the field of view of the robot can be connected using a motion primitive similar to the previous one that we call here F2. So we basically need to find are given that the initial state has to be inside of F1, the initial trajectory, and we want to find the minimum time T that connects the new trajectory with the desired point so that the robot arrives again with zero velocity and acceleration and jerk. So in here, we also illustrate the possibility that there is a dynamic object that has entered the field of view of the robot. So in addition to verifying that the point is collision-free with respect to obstacles in the map, to static obstacles, it also needs to take into account dynamic obstacles. So we may know, for example, the velocity, may be able to see the velocity or the other higher derivatives of the agent, and make sure to choose a point that is doesn't take the robot closer to the dynamic object. Optionally, we can also, if there is communication, we can, the robots can cooperatively plan a trajectory that for each agent that is not only collision free, but also they can try to minimize some common objective, like minimizing the maximum travel time for all the agents. And we propose here to do it using an algorithm called DRRT star from Shum, Solovey, and Dobson. So we implemented this in a simulation environment here. So the robots are following the algorithm I just described. And in this case, they are trying to find a person that is hiding here in this environment behind the red object here. And you can see one of the robots already found the person. The others are still exploring and following the same strategy of finding points that are safe inside of their field of view and coordinating with each other using the DRRT star algorithm. So the third algorithm that I want to describe is, I'll call it kinodynamic planning. And this is a planning-based approach that takes into account the dynamic constraints of the robot. The other method also takes into account the dynamic constraints, by the way, I forgot to mention. So the idea here is that we are given a path or a linear segment of a path that is defined by the current point where the robot is located and a target location that is connected by a line. So what we want to do is the robot to move along the line without separating more than a safety radius from the line. So the way to do this is by designing a virtual controller that induces an equilibrium point, and then we have a strategy to move the equilibrium point along the line from the starting position to the goal, such that the robot remains inside of the invariant set that will maintain the robot in the free space with an error no greater than some epsilon that is prescribed. So compared to other similar techniques like contouring, for example, or funnels from Drake. In this technique, there is no optimization that is done online. So what we need to do is some LQR control design offline and Lyapunov analysis. And then online, all we need to do is to integrate differential equations. So the implementation is very fast, and once we use an algorithm such as RRT to explore the space in 3D, we can find vertices and then connect them using the dynamic approach that I just described. So what happens when there is another dynamic obstacle in the environment is that we have a strategy to slow down or change adjust the velocity of the tracking of the particle motion by taking into account the relative distance between the two agents. So if they are close to each other, then one agent will slow down while the other is allowed to continue. So in order for this to work, what we need to do is to define a hierarchical system. So when robots with higher priority have the preference, and robots with lower priority have to slow down and give priority to the other robot. So we can also use this coordination strategy or this planning technique to resolve difficult situations. Like, for example, when you have a passage or a narrow passage where two robots want to go, then using the planning technique that I described, using the 3D sampling strategy to search the space for alternative alternative paths, then using the hierarchical approach to determine which robot needs to replan and which robot is allowed to continue in its current path. So we implemented this in a simulated forest environment shown here, and you can see that the robots can resolve this very difficult problem in a very dense environment where there are pockets where that generate that prevent the robots from continuing forward, and they have to back up and replan and so on. We also implemented the method in a simulation where we want to explore a scenario that and this can be part of inspection, for example, that this is a task that is requested by the business units where they want to have a solution to explore to inspect power lines and inspect the towers of the power that carry the power lines, or for example in some search and rescue scenario. So here you see the bird's eye view of the 5 agents, and in the right hand side you can see some view from the onboard camera that is used by the robots to navigate environment. So all the sensing and processing is done on board by the robots. So in the final part of the talk, I just want to mention some implementation aspects that we have found in that are interesting and important for multi-robot systems. First, for the implementation, we used a framework from Intel called Intel Edge Insights for Industrial. So our algorithms are integrated into this framework. And basically what we did was implement a complete robot system, autonomous robot system, into a container that can be directly installed into a computer, connect the sensors like RealSense cameras and IMUs and so on, and you can immediately have an autonomous drone. We also developed a module for running the simulation in the gazebo simulation, also in a Docker container. And all of these containers, for example, each container can run the code for one quadcopter, and they are all connected using the EII bus, message bus, that is similar to ROS. It uses similar messages. And of course, we can also implement this using ROS as well. So another key aspect for this system is the robust trajectory tracking controller. So I'm not going to go into much detail. I just want to mention that the controller is based on a sliding mode control, and it's able to handle large disturbances, for example, from wind perturbations, also unknown parameters or variation in the parameters of the system. And you can see here some images that illustrate this robustness. So with respect to very strong wind disturbance that is simulated here by the person, and this allows the robot to move very close to each other. Sorry, to move really very close to each other and remain and be able to follow precisely a trajectory that is specified. So finally, I want to mention the mapping is also very critical for this system. And for our implementation, we developed a linear octree approach, where the map is implemented using a hash function that includes the 3D position of each voxels, but also includes the level of the voxel in the hierarchy. So while the linear octree only typically only maintains the branch nodes instead of the whole hierarchy of the octree, by integrating the voxel level into the hash function, we are able to take advantage of it for example, collision checking. So due to the voxel structure that is implied, we can have a solution that is able to check paths of a length in a way that scales logarithmically with the size of the line that needs to be checked. In terms of updating the map, we also devised, we used the grid mapping algorithm to maintain a probabilistic state of occupation of all the voxels, and we use a space carving technique to very quickly process all the point clouds in each frame in under 1 millisecond. Also, one thing that is very critical in terms of having multi-agent systems is to be able to delete the non-dynamic obstacles from the map. So we implemented also a very efficient method to remove these known objects, for example, other drones from the map. And finally, a technique also to process the polynomial trajectories by segmenting them into line segments that have a prescribed maximum radius. So with this, I'll conclude, and if there are any questions, I'll be happy to answer.
Thank you very much for the talk. Very interesting. And I just wanted to ask about the way that these sort of like agents start to avoid each other. Have you used anything else like different path planning, or is it all just like velocity-based avoidance?
Well, it's we have tried other approaches. The approaches that we they are already all based on planning. So we haven't done a lot of trying other decentralized approaches like reciprocal velocity obstacles and such. We have found that we can plan fast enough. So for example, in under 10 milliseconds, so that we can generate trajectories that have some safe characteristics that take into account the full nonlinear characteristics of the maps, and this seems to work well for us.
Thank you. And do you have time for another? Yeah, and the other quick one is, have you done this, the avoidance, I didn't really see, with like multiple vehicles as well, or was it just like a one-on-one avoidance?
No, there's also with multiple vehicles. So we did show the example where there are 15 simulated agents in a simulated forest environment. We did some experiments with physical drones in the lab, but we were limited to 4 or 5 drones only.
Nice. Thank you very much.
All right, let's
Thank you.